Hello guys, welcome back to lecture series on linear algebra. Guys, in our today's video, I'm gonna explain to you all properties of eigenvalues. Myself, Dr. Swapnil Shinde, and welcome back to lecture series on complete linear algebra. Okay, so without further ado, let's get dive into our today's lecture. I'm gonna explain to you all first of all what are the actually important properties for eigenvalues. Okay. Mostly you can use the characteristic equation, standard equation for finding the eigenvalues, like a determinant of a minus lambda I which is equal to 0. That way also you can find. But some of the matrix, they are standard. Okay, so easily we can define their eigenvalue by looking them only. Okay, so these are the trick very important for your competitive exam. Okay, not only in a competitive exam, you can apply in your regular exams also. Okay, yes. So in our last lecture, guys, I explained to you all the matrix which is upper triangular or upper triangular. Okay, upper triangular, lower triangular, or diagonal. Okay, so matrix upper triangular, lower triangular, and diagonal, which are having diagonal entries as eigenvalue we define as the lambda. Okay, diagonal entry as a lambda. Okay, this one is the first important property: upper triangular, lower triangular, diagonal matrix. Okay, diagonal matrix which are having diagonal entry as a lambda means eigenvalue. Okay, yes. Now next very important property for eigenvalue. Okay, so whenever we add all of the eigenvalues, whenever we add all the eigenvalue, consider lambda 1 is first eigenvalue, lambda 2 is second, lambda 3 is third, and up to lambda n eigenvalues are present for matrix. Okay, whenever we add all the n eigenvalue, we write a trace of matrix. Okay, that means whatever the matrix are there, we write a trace of that matrix. Okay, so whenever you add all the diagonal entries equal to addition of eigenvalue, that means we write a11 plus a22 plus a33 plus an. Okay, that means addition of eigenvalue which is equal to addition of a diagonal element. Okay, that means addition of eigenvalue is a trace of a matrix. Okay, always remember that addition of eigenvalue is a trace of matrix. Very important point. Third, okay, multiplication of eigenvalue. Okay, so how we define multiplication of eigenvalue? Like a lambda 1 multiplied by lambda 2 multiplied by lambda n. Okay, so whenever you multiply all n eigenvalue, we get the determinant of a matrix. Okay, consider that matrix as A. Okay, so if you multiply all the eigenvalue, you will get the determinant of a matrix. Okay, these are two very important remarks. Okay, very important. Okay, that one is useful for finding the eigenvalues, eigenvectors. Okay, yes. Now, so next important property, if a lambda is a non-zero, okay, lambda is a non-zero eigenvalue, okay, of matrix A. Okay, lambda is a non-zero eigenvalue of a matrix A, then we write 1 upon lambda is eigenvalue of matrix A inverse. Okay, that means you can easily define the eigenvalue for inverse matrix. Okay, but only condition that lambda need to be a non-zero. Okay, then only we can define. Okay, so you can define for orthogonal matrix. Okay, so if a lambda is eigenvalue for orthogonal matrix, then 1 upon lambda is also the eigenvalue for its eigenvalue. Okay, for orthogonal matrix. Yes. So next remark, fifth. Okay, lambda 1 to lambda n are eigenvalue of matrix A. Lambda 1 comma lambda 2 up to lambda n is eigenvalue. Lambda 1 to lambda n are eigenvalue of matrix A. Okay, lambda 1 to lambda n is eigenvalue of matrix A. Okay, then we write lambda 1 raised to m, lambda 2 raised to m, lambda n raised to m is eigenvalue of a raised to m. That means if you take m the power or second power, third power, fourth power, similarly you have to take that power to their eigenvalues. Okay, so these two remarks hold. Always remember that m need to be a positive integer only. M, okay, m positive integer. M need to be a positive integer only, then it is possible. Okay, yes. So let me take to the next property. Okay, if a matrix and it's a transpose. Okay, so if you take matrix A and the transpose of matrix A, okay, eigenvalue lambda of A which is equal to lambda of A transpose. That means eigenvalue of A and a transpose of eigenvalue both are equal. Okay, that means if you take the transpose of matrix, their eigenvalue and the given original matrix, its eigenvalue both are equal. Okay, that means matrix A and its transpose are having same eigenvalue. Okay, next remark, if lambda 1 to lambda n are eigenvalue of matrix A, then eigenvalue of matrix K. Okay, next, it is very easy guys. Lambda 1, lambda 2, lambda n, these are the eigenvalue of A. Okay, then eigenvalue of K times A is a K into lambda 1, K into lambda 2 up to K into lambda n. Okay, that means if A is having lambda 1 to lambda n eigenvalue, that this implies Ka having eigenvalue K lambda 1, K lambda 2 and K lambda n. Okay, yes. Next remark, if lambda 1 to lambda n are eigenvalue of A, then eigenvalue of A plus minus Ki. Next, lambda 1 to lambda n eigenvalue of A. Okay, if lambda 1 to lambda n are eigenvalue of A, okay, then A plus minus Ki are A plus minus Ki having eigenvalue A plus minus Ki having eigenvalue lambda 1 plus minus K, lambda 1 plus minus K, okay, lambda 2 plus minus K, lambda 2 plus minus K, and up to lambda n plus minus K, lambda n plus minus K. Okay, it is very easy guys, not that difficult. If matrix A is having lambda 1 to lambda n eigenvalues, A plus minus Ki gives eigenvalue as lambda 1 plus minus K, lambda 2 plus minus K, and lambda n plus minus K. Okay, so these properties are important guys for eigenvalue. You're supposed to remember these ones. If you want, note it down for your reference. Okay, very important property for eigenvalues. Okay, so I hope you have understood all the properties from eigenvalue, which are very important. So even after, if you found anything confusing, difficult, let me know in my comment section guys. I'll come up with the similar videos. So thank you everyone, thank you for my today's lecture. In our next lecture we go for more advanced points in linear algebra.